And we are definitely not the only ones with this idea of making molecular Tweezer arrays. In fact, the first molecular Tweezer arrays of laser-cooled molecules was made in John's group with CaF. And also with bialkalis, this has been done in Conquidney's group here at Harvard with sodium cesium. There are other efforts also during the cesium. So in 2019, the first molecular tweezers were made, as you've seen this morning, both with laser-cooled CaF and also with bialkali sodium cesium. And this year in 2022, it's sort of the year where these molecular tweezer arrays are scaled up to somewhere between 10 and 50 sites. So for laser-cooled calcium fluoride in our group, we're able to get tens of these tweezer traps earlier this summer, and this also is now has been realized in John's. So the sort of natural next step is that we want to completely determine where the molecules are inside these tweezer arrays. We can do this by rearrangement. And then the next step to make look at interesting physics is to make molecules that are spatially separated from different tweezer traps. So Mike Tarvett already told you a lot about calcium fluoride earlier and how to laser cool it. So here's a level diagram of the lasers that you need and the relevant energy levels. But for the talk today, we'll live down here in the electronic ground state, and we'll live in the ground vibrational state, so B equals 0 here. And all we'll do is that we'll pick two states out of the ground and the first excited rotation of that, so N equals 0 and N equals 2. The important point to remember for today is that CaF is polar, and it has a sizable electric dipole moment of 3 to 1. So it means that they do have non-zero electric dipole interactions. The other fact to remember for this talk is that optical cycling only works for the first excited rotation of state, and this actually will allow us to have some sort of state dependent. So zooming in a little bit more, instead of actually writing out the full state, for this talk, we'll have a two-level system made of spin up and spin down, where spin up is N equals 1 and spin down is N equals 0. For the next few slides, I'll tell you why we want to pick our pseudo-spin bases in N equals 1 and N equals 0, and how we can actually specifically make them interact and entangle. So fundamentally, the interactions arise from this dipolar interaction Hamiltonian, which goes as 1 over the separation distance cubed. It's anisotropic, and it depends on the product of the dipole operators on each of the molecules within the pair. Now, specifically for us, we actually do not align the molecules. So what this means is that in the absence of this electric field that can align it, the molecule has no left frame dipole moment. Another way to think of it is that classically there is no energy shift. So the dipolar Hamiltonian has no diagonal returns. But as we all know, states can have transition dipole moments, specifically between N equals 0 and N equals 1. This transition matrix element is non-zero. So now if I have two molecules, what this means is that as long as I flip the spins of both of the molecules, then that process is in principle allowed. So I can flip two down molecules to two up molecules, and I'll just call that the matrix element J over 2. Now I can also flip the spins of molecules aligned as down and up to up and down. So if I write down the full Hamiltonian, I get these off diagonal terms, J over 2. But in our case, if you put in the typical length scales of microns, this coupling is actually fairly weak. It's about anywhere from 10 hertz to about a kilohertz. And what you find out is that this coupling is actually much weaker than the rotational splitting, which for us is about 100 gigahertz. So what this means is that this process of flipping 2 downs to 2 ups is actually energetically forbidden. It's highly suppressed, which means we can, to a very good approximation, ignore this coupling. And then if you go to the interaction picture, of, effectively the rotating frame, you end up with a very simple Hamiltonian that only couples up-down to down-up coherently with J over 2. So essentially we are only left with so-called resonant spin exchange. These two configurations have the same energy. So now, if you write this in terms of spin operators, this actually becomes a S minus, S plus, plus S plus S minus Hamiltonian, which is equivalent to an XX plus YY interaction term. You can see this easily because when the system hops over between the two configurations, we are simply just exchanging a rotational excitation. So this means that another way to look at this interaction with resonant spin exchange is that we have implemented the building block of a quantum spin model known as the Manifest model. And this interaction, if you apply it for a very specific time, can actually lead to entanglement of two molecules. So one way to see this is that if I start the system in down up, it will resonantly flop between down up and up down. All I have to do is stop halfway in between. I'll be in a superposition of these two states, and that actually is the maximally entangled state of these two molecules. So now this interaction Hamiltonian, in fact, can be used to realize an entangling two-qubit gate as first proposed by Compton a few years back. And this entangling two-qubit gate is called the I-swap gate, which, together with single qubit rotations, is actually sufficient for universal digital quantum computation. So essentially what we want to see is see that we can actually implement this Hamiltonian between two molecules, and we can actually show that it behaves the way that we expect it to do. Right, so now that we understand how the electric dipolar interaction can give rise to this effective Hamiltonian, let's move on to what we actually do in the experiment. So our system consists of laser-cooled CaF molecules. So we'll follow the typical way of making cold CaF molecules. So we use Mike Target's typical way of generating CaF molecules chemically. We slow it down with Cheuk slowly, make a DC mop, apply various types of cooling, optical trapping. There's some acrobatics with transport, which I won't get into in the interest of time. We essentially move these molecules to where the tweezers are located and try to pick up single molecules out of this optical trap. So this actually is a bit challenging because these traps are actually smaller than a micron. So earlier this summer we were able to see these single molecules randomly loaded into these arrays of 20 to 30 cells. One thing to remember is that this loading process is actually stochastic. So a priori, we don't know which traps are actually unlocked. So this actually will be our starting point today. And then I'll tell you about all the steps that we have worked on since having randomly filled molecular tweezers. So the first thing we want to do is try to control the initial state better. And there's two aspects to it. The first one is that we want to remove all configurational entropy. So we want to deterministically have molecules at the right places. So the way we do this is that we first take a peek by taking a non-destructive image of what is loaded. Then based on what we find here, we then, in a few milliseconds, move the occupied tweezers to the right location. For example, here we make pairs of molecules that are well separated. Now, to determine how well this process actually works, we can also program in uniformly spaced linear arrays. So here are example images, single shot of molecules that are rearranged into these uniform arrays. And by plotting the success probability versus the chain length, you can actually find that the rearrangement fidelity is a little bit above 97%, so it should be 97.4%. So now, with rearrangement, we can actually know where the molecules are, but that is still not good enough. Because during laser cooling and imaging, the molecules are actually spread out over a bunch of hyperfine states in n equals 1. There are not that many here, but there's still 12, and we have to put all of them into a single quantum state, single internal hyperfine state. So to do this, we actually implemented a way to optically pump these molecules into 2-2, and similar to what Mike Target does, we pump them into this particular state, use a microwave transfer to hide them in n equals 0, and then blow away all the molecules that weren't successfully pumped. And then with the final microwave sweep, we can put them all into one of these states, which we'll call. Because of this clean-out pulse, the errors that we get primarily appear as empty tweezers rather than molecules in the wrong internal state. And this actually is a nice feature. So the overall fidelity of this whole process ends up being about 82% in what we put on the archive. This is primarily limited by technical errors, and sort of even in the past few days we have substantially improved these numbers to somewhere around 90% or so. And with further work, we think we can actually push this a little bit higher. But for the talk today, this doesn't really matter as long as it gives us good data rate, because we can actually divide it. Okay, so with optical pumping and rearrangement, we essentially have fully prepared the occupation and the hyperfine state of the system. So now we can go ahead and look and try to see if we can make these molecules interact. So all of this work of, all of these techniques of laser cooling molecules, trapping them, pulling them and imaging them actually built upon work that has been done by Mike Cheuk and John Cheuk, and also in general, finding work at Dave Cheuk on these molecules. So we really benefit from a lot of previous work. All right, so let's see how we can see interactions. Before we look at interactions, one very important thing to optimize for is the coherence time between our two states of choice, up and down. As you have heard already, getting long coherence times between different rotational states is actually a bit tricky for optically trapped molecules. The reason is that typically different states in the molecule feel slightly different trapping potentials. Now in tweezers, the trap depth is quite deep. They're on the megahertz scale. But we want coherence times that are long compared to our expected interaction. Now interaction is only tens of hertz to maybe 100 hertz. So this means that we want to minimize the differential light shifts such that the decoherence rate is on the level of, let's say, 2 hertz out of this total track depth. So to do this, we actually use a technique that was first demonstrated and delivered last year on pseudo-magic tracking conditions. So in our case, essentially by orienting the magnetic field and the polarization appropriately and using the right track depth, we can minimize this differential light shifts to an acceptable level. There are other effects of tightly focused tweezers that I won't get into in the interest of time. All right, so we go to one of these, to this predicted theoretical pseudo-magic condition, and we went to look at what coherence times we would get. So the way we do this is that we just program in isolated single molecules and perform Ramsey spectroscopy. So in short, we essentially apply pi over 2 pulse, put it into superposition of up and down, wait for a while, and then apply another pi over 2 pulse with variable phase delay. So the resulting contrast of these Ramsey fringes actually directly tell you the coherence. So without doing anything special, we find a coherence time of about 2 to 3 milliseconds. But just adding one spin echo, so one pi pulse in between, we actually can extend the coherence time by about a factor of 10 to 30 milliseconds. So it's sort of better, but not quite good enough to see a lot of oscillations, coherent interaction. But what you can do is actually implement dynamical decoupling, which is sort of well known in other systems of NV centers, just say qubits. So we in particular use this dynamical decoupling sequence called XY8, which essentially is just a bunch of pi pulses. And once we do that, we find that this T2 time is increased by another factor of 10 to about 200 milliseconds. Now this number actually is still significantly limited by microwave pulse errors, which they can be improved in the future. So based on these timescales, we think most of this decoherence is just from ambient magnetic field fluctuations, which potentially can also be. So with 200 milliseconds, we should have enough coherence time to see these dipolar interactions that are on a few millisecond time. So let's see how we actually see coherent interactions. So again, we initialize molecules in the spin-up state, but instead of starting with isolated molecules, we'll start with pairs of molecules because we control the initial configuration. So we put them into closely spaced pairs where each pair is well separated. Now, if you think about the Ramsey sequence, starting with 2 particles in spin-up, if I apply pi over 2 pulse, and then immediately apply another pi over 2 pulse, the 2 ups will be converted to 2 down. But if I wait for a little bit of time before I apply the second pi over 2 pulse, this superposition of up, down, and down, up can actually acquire a phase. Because remember, a spin exchange Hamiltonian has these off-diagonal J2 terms, and up, down, plus down, up is actually one of the ITAMPs. For example, if I wait for a time where this accumulated phase is pi, I get a -1 sign here, and instead of returning to down, down, I would actually completely return to up. So what this means is that I can just look at the probability of detecting 2 molecules, both and up, and see if it actually oscillates. And if it does oscillate, the oscillation frequency will directly tell me what this is. So that's what we set out to do. And because we have the capability to detect individual molecules, specifically at n equals 1, we can actually find this P alpha probability. And indeed, when we implement the sequence, we do see oscillations. They don't last forever, but at least for a few cycles. So that's good. So to make sure that these actually are due to dipolar interactions, we can also vary the spacing between the two molecules in the pair, because we have full control of where these molecules are. So we scan it from about 1.2 microns all the way to 2.3 microns. And we fit these curves to find out what frequency these wiggles are. And in fact, when we plot it versus distance, it agrees quite well with what we expect and follows roughly one another. So these oscillations actually are evidence for coherent interactions between individually prepared molecules. And that's sort of the first observation for any individually prepared molecules, and also the first observation for laser-cooled. But they're not the first observation of dipolar interactions. Actually, about 9 years back in Genius Group, they actually had seen similar oscillations using molecules. And recently, this has also been seen in quantum gas microscopes. So with these dipolar interactions, we next try to make a 2-qubit gate to entangle molecules. So if you look at these oscillation curves, if I just stop exactly halfway up the first wiggle, this actually creates a Bell state. In particular, if you sandwich interaction time between two 502 pulses, it exactly realizes an I-swap gate that Coherent proposed, and it actually creates this particular Bell state of down, down, plus up. It won't go into details here, but you can actually measure the fidelity exactly of creating this Bell state simply by measuring the population and also the coherence and the density matrix. So based on these measurements, we can find that the raw fidelity is about 54%. If you correct for state preparation, so primarily for empty sites, we actually get a span corrected I-swap gate fidelity of 80%. So this actually is sort of at the same level as other platforms like Rydberg atoms and superconducting qubits 5 years back. Not right. So it's sort of good for the first demonstration of such a type of gate between individually prepared molecules. So now that we have a Bell state, we can also ask how does it behave. So we measure how long it survives. So we just create it, hold it for a while, and measure the fidelity. And we find that it lives for about 100 milliseconds, which is roughly what we expect from the single particle coherence. Now, as Yumi mentioned earlier, with dipolar interactions, they fall off pretty quickly. And you sort of have a connectivity problem. So one way to get around it is to actually first entangle the molecules and then move them around to somewhere further. So we went ahead and checked how long the entanglement actually survives. So we made this up plus down pair, and then we pulled it apart. So we think of this sort of like an EPR pair. And then we again hold it for a while, measure the fidelity. And essentially, to within the experimental error bars, we don't really see any difference. So this actually could be a nice capability in the future of obtaining more connectivity in larger systems. And recent work with Rydberg atoms actually have used this ability to move quantities around to create useful states like clusters. I'm sort of out of time, so all I'm going to say is that we have realized building blocks for digital quantum computing. These type of parity oscillations actually also tell us that we have implemented an anti-ferromagnetic spin model. And also, you can actually directly see the twofold enhancement in phase sensitivity of the Bell state just from these oscillations. And with that, I come to my last slide. I've been telling you about how to use molecules, laser-cooled molecules, to do quantum information processing and to simulate quantum spin models. Then maybe we should now think of the ability to entangle molecules to offer us something new. We can think of entangled molecules as a new quantum resource. And if you think of it that way, with further work in the community of extending these techniques to larger molecules, it potentially opens up new possibilities such as precision measurement that go beyond the standard quantum limit, and also exploring molecular collisions and perhaps chemical reactions using perhaps entangled pairs of molecules. So with that, I come to the acknowledgement slide. Again, the people did the work. I want to acknowledge the funding sources. And I also want to advertise that along the way, we also have looked at various new ways of controlling and detecting molecules, some of which tackle some of the problems that we mentioned today. With that, I would like to thank all of you for your attention and take any questions.
All right, we don't have that many minutes for questions, but he is an organizer, so.
So if you had every tweezer site occupied, and each one is interacting with the neighboring pair on each side, could you not get all-to-all connectivity this way?
You can use this to send information from one side to another, but there actually are, in the 1D system, they are bound to that.
So the edge will be the bound.
Yeah, but for example, if you use a cavity like we propose, then immediately you can couple them over bonds.
Go ahead. Yeah, you.
Yeah, excellent. First question is the uniformity of the entangling fidelity, how good is the uniformity across all pairs?
I don't think we have looked into the uniformity, so potentially it could be better for one pair or another.
And then I guess the second question is, where do we go to 99%?
So where we go to 99%. So,
I mean, what is it?
yeah, to be honest, I would say I can't say fully what the limitations are. One of our guesses is that it's actually thermal motion. What we do see is that the collision, the spin exchange oscillations snap quicker when you're closer, more than you would expect from the independently measured coherence times at the same distance. Now, if you have thermal motion, then the molecules are a variety of different distances, and this effect becomes increasingly stronger when you get closer. This leads to effective dephasing, which can end up limiting the fidelity. I would say some preliminary calculations show that it's at the same decoherence rate, roughly, that we see, but we don't have conclusive data that says this is the mechanism. There's some subtleties in what you assume about the decoherence.
Just maybe a follow-up question about the coherence time. So I see you've chosen qubit states that to first order have no tensor shifts, but I think at the intensities you're using, there's like hyperfine mixing, which means you do get some differential AC Stark shifts. And I'm wondering whether you need to be at such large trap depths, or whether you can actually lower the trap depth. Would that help?
So I didn't mention that, but we do lower the trap depth to about a tenth when we load the tweezer. They're at, I think, about 130 microkelvin. So this magic condition is only pseudo magic. So for that magnetic field, in that orientation, around 130 microkelvin of depth. Minimally insensitive.
Go ahead.
Very impressive notes. Congratulations, first of all. Because it works so nicely, do you plan or do you think you can make 3, 4, 5 particle entangled states? Scale it
Yes.
up? I mean, you have the tweezers, you have everything available somewhere.
I think the answer is yes, but the probability will drop. And taking the data will be more and more painful. Mostly, I think it's state preparation. So with 90% state prep, you want to make five particle system, you're immediately down to 50% success rate. Now, if you only have 80% entanglement between each particles, then you have to take roughly 0.8 to the 5. So you can, but it will be more challenging.
But there's maybe hopes that you can improve on the state preparation.
Yes. So I think once we improve these by substantially, then that's something possible.
But I guess the question to follow up, like, for this multi-particle entanglement, do they have to have the same distance? Like, what kind of geometry? Like,
I guess you can have every geometry.
well, but the interaction is distance dependent. So do they have to have the same interaction, or they can be a chance where?
Yeah, so there are a few ways to do it. You can, do spin squeezing and do collective entanglement, or you can really do a gate-based approach, which might not be as efficient. But once you have programmability, you essentially can generate any state, entangled state that you want. It's just a matter of whether you generate a significant
All right, there's one last question. Timur, do you want to go ahead and get set up maybe? Go ahead.
Could you not improve on your state preparation by instead of blowing them away, just imaging them so that you know that you've done a mistake that you see?
Yes, in principle, yes. Our imaging is not completely lossless, so you lose even with the non-destructive imaging, plus any sort of wait time between the receptor and the other, losing about 2 or 3%. So, the optical pumping is working fairly well, but it's a little bit like death by 1,000 cuts. You lose a few percent in the microwave, few speeds, 10%. But all of these, I think, are technical.
All right, well, let's thank Lawrence again for an amazing